All right, in this video, I'll give an overview of statistical hypothesis testing, specifically the most common method called null hypothesis significance testing. In short, the idea is we're going to assume that there's no effect or no difference or no relationship between the variables, that nothing interesting is going on, and then we calculate what kind of sample data we would be likely to see if that was the case. Then we're going to collect our real sample, and if our real sample doesn't fall within those expectations of what we would see if there was no effect, then we'll reject the idea that there's no effect, and we would conclude there's probably a real effect here. But that might have sounded a little confusing, so let's work through the idea a little at a time. We're going to start with an example. Imagine I've got a scientific hypothesis. Let's say I work for a pharmaceutical company and I think my new drug Memorex is going to work to improve memory. So I think it has an effect. I'm going to give Memorex to some randomly selected people and measure their memory afterward. But in order to know if it works, I might want to compare them to the general population of people that I randomly selected them from. So let's say I already know from past data or a huge control group that the general population scores on a particular memory test, let's say the Stone memory test, are normally distributed with a mean of 50 and a standard deviation of 10. That's just what memory is like for people in the population overall. Now, I want to know if my new drug will raise people's memory beyond that. So let's say for our study, we give 36 people Memorex for a few months, and then we measure their memory at the end of that. Maybe we find a mean score of 55 in our sample. So the question is, based on this data, should I conclude that Memorex works? I mean, our sample has an average of 55, not 50, so these 36 people are definitely higher than average. But there's a couple possibilities here. Possibility one is that, yeah, Memorex does work, and that's why my sample scored higher than 50. But possibility two is that Memorex actually does not work. Maybe we just happened to sample 36 people who already had slightly above average memory, just by random chance alone, and thus the pills that they took didn't do anything. What we've got here are two mutually exclusive hypotheses that would both explain getting this data where our sample has a mean of 55. So we might call our hypothesis H1. We think Memorex works, so we're hypothesizing that our 36 Memorex takers, the sample from a population, we're assuming it's a sample from a population that has a higher than average memory. So Memorex takers in general would have higher memory than the general population. That is our hypothesis. It's just saying the population of all Memorex takers would have an average of, an average memory level greater than the average memory of the general population. By the way, the Greek letter you see here, that's mu, like mu, but pronounced mu, it denotes a population's average. So it's just a mean value, but not for a sample, for a whole population. So H1 is that mu of the Memorex group, so the population average of the Memorex group, is greater than mu of the general population. But the other possibility is that we might call this the null hypothesis, null for zero or nothing. We might be seeing this because our sample isn't actually telling us about Memorex working in general. Instead, in this hypothesis, our sample is from the same as the general population. Maybe Memorex even makes it worse, but at the very least, it's not better. So that would be the null hypothesis, H0. Basically, it's the exact opposite of our hypothesis, H1. It's the idea that Memorex doesn't work, that Memorex is no better than the general population. It's equal or could even be worse. That's the less than or greater, or less than or equal to sign. Okay, so the null hypothesis will always have some form of an equals sign in it because it involves the possibility of no effect. Like in this case, that our Memorex group is equal to the general population, but it could also have a greater than or equal to sign or a less than or equal to sign as long as it has the equals somewhere in the null hypothesis. And whatever it is, our alternative has to be the exact opposite to match that. So H1 will always be either a less than, a greater than, or a does not equals sign in it. You can think of it this way. As a pair, H0 and H1 need to be mutually exclusive and they need to be exhaustive. So they should not overlap in any way, but they should cover all the possibilities. So if H0, the null hypothesis is that they're equal, if H0 has the equal sign in it, then H1 should be the opposite of that. It should be that they're not equal. Or in the middle box here, if H0 is that one group is greater than or equal to the other group, then H1 should be that that group is actually less than. So you can see how these are opposites of each other. In the rightmost box, maybe you set it up where the null hypothesis is that group A's mean is less than or equal to group B's mean, then H1 will be the opposite, that A is greater than B. Regardless, we're going to end up with two hypotheses. It'll be one of these three setups. We're going to end up with two hypotheses, the null hypothesis and the alternative hypothesis, and one of them has to be true, and only one of them can be true. So it's either one or the other. So let's say for our Memorex example, maybe I have some reason to suspect that Memorex increases memory scores, that people taking it would have greater scores than the general population. So that's H1 here, my alternative. But that means the null hypothesis needs to be its opposite, that the Memorex population would be less than or equal to the general population. In other words, just not greater, not better. So the logic of significance testing is going to be that we will assume the null hypothesis is true. Just temporarily, we're going to pretend. We're going to assume the null hypothesis is true. And from that, we can calculate the probability we would have just by chance gotten a sample mean this far from 50, just by randomly sampling the general population, like if the null was true. In other words, first we pretend the null hypothesis is true and that Memorex doesn't improve memory. If so, what are the odds we would take a sample from that and get a sample mean of 55 like we did? So technically what we're doing is looking at the distribution of sample means, of all possible sample means we might get from the general population, the null hypothesis, meaning the distribution of all the ways a sample of this size might come out even when Memorex doesn't increase memory. And then if our sample is very unlikely to happen in that case, if our sample just wouldn't happen very often in that case, then we reject that case. We reject the null hypothesis. So this is kind of a weird process, but you have to think of it as always starting with the what if of pretending the null hypothesis is true. Then we can calculate what samples would look like when people on Memorex don't get a memory boost, when the null is true. What would samples of 36 people taken at random tend to score for their average memory? What would these samples tend to look like? If it's common to run into samples with a mean of 55, like we got, then we would have no reason to reject the null hypothesis, right? We'd get sample data like this all the time. But if it's not common under the null hypothesis, under that assumption, if it wouldn't be common to run into samples with a mean of 55, like we found here, if it's not that common when the null hypothesis is true, then we reject the null hypothesis. So at its heart, this process of statistical hypothesis testing, it works by rejecting the null. Like rejecting the null hypothesis if the data that you got would be unlikely when the null is true. And because the alternative hypothesis is the exact opposite of the null, and together they're the only possibilities, then yeah, if we can reject the null hypothesis, then we can accept the alternative hypothesis. So if we reject the null, then we are saying we do think Memorex works. We do think the drug improves memory. Do note that this whole thing is probabilistic. So probability can tell us, that the null is very unlikely to have produced our data, but it can never prove 100% that the null is wrong or wouldn't make this data ever. So we're going to avoid the language of proving things, and we'll just say supported or accepted. Kind of like we're accepting the alternative hypothesis as likely rather than proving it when we reject the null. So we can't 100% prove the null to be wrong. We can't 100% prove that it's not the case. But if the null is very unlikely to give data like our sample, then our alternative hypothesis, the opposite, is supported. It's very likely. It's never proven, though. Okay, Now, just a quick practice example, getting used to this language of a null hypothesis and an alternative hypothesis. Remember, our setup of hypotheses has to be one of these three boxes. If you have a direction in mind, a reason to think a particular direction will happen, then you might choose the middle or the right side box, where your alternative hypothesis has a direction built into it. We did that with Memorex because we would only care and only market the drug if there was evidence that it increases memory. We wouldn't have been interested if it was in the other direction. But other times, maybe you don't have a direction to your alternative hypothesis. Maybe you just want to know if the groups are different in some way, if they're non-equal. Like, I don't know, is there a difference between men and women in their ideal television size? Maybe you don't have any reason to expect it to be one way or the other. You don't expect men to be bigger or smaller in their preferences for TV, but you want to know if the genders differ in that preference. So for that, you would use the left box as your hypothesis setup, where you're saying either they're equal or they're not equal, and that's what you're going to try and find out. So let's try this stuff with a made-up example. Let's say biologists know that American eels are 20 inches long on average. That's the population mean, which we call mu, right? The mu for American eels is 20 inches. And let's say that's been known for ages. We just know that. Now let's say Dr. Octavius discovers a new species out in Florida and hypothesizes that the new species is shorter than normal American eels. There's a reason to think he's got this suspicion that they're shorter on average. So maybe pause and try writing down her null hypothesis and her alternative hypothesis before moving on to the next bit. So she is hypothesizing that this new species is smaller. So we might say her alternative hypothesis, her H1, is that the population mean of the new species is less than the population mean of American eels. Now I've used a subscript here to put new species or American eels on each side, but you can just write it out in words if that's easier. The point is, her hypothesis has a direction. We would say it's directional or one-tailed. We have one direction in mind. But that means that the matching null hypothesis, the H0, the one that always has to have an equals sign somewhere in it, it's got to be that the population mean of the new species is greater than or equal to the population mean of American eels. So the null hypothesis is that the new species, mu, is same or bigger compared to the American mu. Now remember, the null hypothesis is always the one with an equals sign in it. But also, note how the two hypotheses we've set up are opposites. They go together, they complement each other. So they come from one of the boxes of options up top there. If I am suspecting a less than relationship in my H1, then I need to put a greater than or equals to sign in my H0 to go with it. Now, obviously, since we were told the average population length of American eels, you might have just put 20 inches in there, and that would have been totally fine, right? Like, she's hypothesizing these new eels are less than 20 inches on average, so the null is that they're equal or greater than 20. Okay, but either way, we still would need to run a statistical test on our sample, some sample of these new eels, to see if there's enough evidence to rule out the null hypothesis, to reject it. Which means we're going to do our process here by temporarily assuming the null hypothesis is true. We're going to pretend the null hypothesis is true and use probability, or a statistics program, to calculate how likely it is we'd get a sample of new eels that are as short as our sample is, as short as our sample ends up being on average. And if it's very unlikely that we would see a sample like our sample when the null hypothesis is true, then we rule out or reject the null hypothesis. But what counts as very unlikely? Like, when should we reject the null hypothesis? And honestly, we can just choose a proportion here that seems to us very unlikely. Now, it's mostly a convention, but in most sciences today, the default is to choose 5%, to choose a proportion of 0.05 as our definition of what's unlikely. Whatever number we choose, that's called the alpha level. But if it's just not mentioned in a study, if you're reading some peer-reviewed journal article and they don't mention the alpha level, you can just assume the researchers used the standard and common 0.05 alpha level. What that means is that when we're pretending the null hypothesis is true, when we're assuming for a moment that the null is true, we can use probability to create a graph like this, a distribution of all possible sample means that we would get from sampling the null population with, whatever sample size we're using, and you can figure out what sample means would be really unusual, really extreme. What sample means would be least likely to happen if the null hypothesis was true. And that's what's highlighted in blue here. So we've put 0.025 or 2.5% on each side. That's just so it adds up to cover both the blue sides combined, cover the most unlikely 5%, the most unlikely 0.05 as a proportion of all the sample means we might get if we took a sample of the size we did when the null hypothesis is true. And if our sample mean, when we actually do a sample and calculate our sample's mean, if it's that far out, if it's that far different from what we'd expect, that unlikely when the null is true, we'd be like, oh, this is pretty unlikely when the null hypothesis is true, so let's reject the null hypothesis. That is the basic logic here. So the actual cutoff numbers of what counts as a sample mean that's far enough out there, that you can calculate by hand, like if you take a statistics class or something, it's really easy to learn, or you can just have a computer program do it for you. But this whole graph and deciding the cutoffs of what counts as quote-unquote unlikely, that just comes from probability theory based on the what if of assuming the null hypothesis is true. And again, by convention, we consider the most unlikely 5% as our cutoffs for what's unlikely, as our cutoffs for when we're going to reject the null hypothesis if our sample is way out here in the pretty unlikely region under the null being true. Now, as I said, you could pick a different alpha level as long as you make that choice before you collect your data, just so you're not biased in choosing a cutoff after the fact in a way that might make your results align with your preconceptions. So you don't have to choose 0.05, but that's the most standard. So perhaps to be more careful and strict and extra conservative, you might pick an even lower proportion as what counts as unlikely enough to reject. So you might pick something like 0.01 instead of 0.05 before you start your study. You would just have to report and tell people that's the alpha level you used. Or you could be less strict. If it's like a low stakes situation, you could choose a cutoff like 0.1. But those, by the way, are not nearly as common. Mostly you might see something like that in an exploratory or a pilot study or something like that. Because if you use 0.1, which by the way is 10%, that means if your sample mean falls anywhere in the 10% least likely sample means that would happen if the null was true, you would be rejecting the null. But at some point, if your definition of unlikely is that widely stretched, then you're not really going to be very confident in your results. So normally we stick to the 0.05 alpha level, meaning like 5%. Now, as I said before, your hypothesis might be directional, what I called a one-tailed hypothesis, meaning you're coming at things to explicitly test one specific direction. Like in our Memorex example, we specifically were looking to see if the sample mean was far enough out in one direction in terms of what we'd expect if the null hypothesis was true. The Memorex group needed to be high enough in that one direction for us to say, whoa now, that is quite unlikely when the null is true, and thus to rule out the null hypothesis. On the other hand, sometimes a non-directional hypothesis, what we often call a two-tailed hypothesis, might be more appropriate. Maybe because you're not coming into it caring or expecting about a particular direction. Maybe you're just testing if there's some evidence that the populations are different, that the groups are different or just unequal in some way. Maybe it could be that the sample is unusually above or unusually below what we would expect if the null hypothesis was true. Maybe either of those would be interesting, and either of those in this case would make us reject the null hypothesis. But now, in that case, our cutoff for what counts as unusually above or unusually below what we would expect when the null is true, now we've got to split that, 0.05, that 5% unlikeliness, into both sides. So we might put 2.5% in each side, right? Half of the 0.05 goes in each side. So we got, smaller little rejection regions. Okay, so to summarize all of that, with a one-tailed directional hypothesis, if we're using the normal alpha level of 0.05, that means we put all 5% into a single tail. So then we want to calculate, or have your computer program calculate, if your sample mean is past the point that's cut off by that alpha level, is out in that rejection region. Whereas for the two-tailed, the non-directional version, if we use our conventional 0.05 alpha level, right, that means you need to put 2.5%, or half of that, right? 0.025 needs to go into each of those tails. And then you're going to calculate again if your sample mean is past either of the cutoffs you set by your alpha level. Now, sometimes you'll see language calling that kind of shaded area here the critical region or the rejection region, because you reject the null hypothesis if your sample mean falls into the region of that region of the null's distribution of sample means. But again, it just means what we're doing here is we're visualizing all possible ways a sample mean might turn out if we took a buttload of samples of that size when the null hypothesis is true. So this whole graph assumes the null hypothesis is true. If it's true, we would see these values as the kind of sample means that we'd get for just all the possible samples we might take of that sample size. Then we check our sample mean, the actual sample we did, and see how far out it is. If we got a sample, we get a sample that looks really unlikely under this graph, we'd say, oh, we'll reject the graph. We'll reject the null hypothesis. But if this graph is showing us a bunch of samples that totally would sometimes show us that things just, commonly would show things as extreme as our sample mean, then we don't reject the null hypothesis. It's only if we're getting samples that wouldn't really occur very often when the null is true, that are out in this unlikely region, that's when we reject the null. Now, if you've got the benefit of a statistics program, you can literally get a calculation of exactly how likely or unlikely that your sample mean would be if the null was true. Like, you plug in your sample size, so it can take into account how big of a sample you took, then probability can generate all the possible samples of that size, so it can generate this curve, and what each one's sample mean would be, then it tells you how likely or unlikely a particular sample mean was. So you could plug in your sample mean, and it will tell you how likely it was to see your sample mean, something at least that extreme, if the null hypothesis is true. And we call that the p-value. So p is just short for probability. So p-value just means the probability of getting a sample mean m that's at least this extreme, right? Our sample mean was m. What's the probability of getting a sample mean at least that extreme or further out in the graph if the null hypothesis was true? That's what a p-value is. Basically, we calculate how far out our sample is on this graph, and the p-value tells you what proportion of the graph is that far or further. If our sample mean m is quite unlikely, like if it's in the little 5% at the tips, we reject the null, which is the same thing as saying the p-value is below 0.05, 5%, or whatever the alpha value we choose is. In that case, we reject the null, because it's just that unlikely that you would get a sample mean m if the null was true. Like literally, if you get a p-value of 0.03, meaning 3%, then it literally means only 3% of the sample means would be this extreme if the null was true. If you get a p-value of 0.001, so 0.1%, it means only 0.1% of samples of that size would have a mean as extreme as what we found, assuming the null was true. Since that's so unlikely, since the p-value is so low when the null is true, right? It's unlikely when the null is true, then we're going to conclude the null is probably not true, and we reject the null. So that's the idea. If the p-value is below 0.05, whatever our alpha level is, but usually 0.05, you reject the null hypothesis. It's just that unlikely, the p-value, it's whatever percent. So if your p-value is very, very, very small, then it's very, very, very unlikely that you would get a sample mean m if your null was true. So that's the idea of hypothesis testing. That's what we're doing with inferential statistics when we try to make a conclusion about the population based on a sample we've taken of a given sample size. So if our sample mean is extreme and unlikely enough, we can reject the null hypothesis. But what if it's not? What if our sample is in the normal 95% of that graph that's totally expected and common when the null is true? Then in that case, we can't reject the null hypothesis. And specifically, we say in that case that you fail to reject the null hypothesis. Basically, we simply don't have enough evidence to reject the null. Now, that does not mean that we accept the null hypothesis as true. We never accept the null hypothesis. We either reject it or we fail to reject it. So if we reject the null, then okay, we can accept the alternative hypothesis, H1, since that's all that's remaining. That's all that's left over. It's the only other possibility. If we reject the null, sure, we can accept the alternative. But if we fail to reject the null, then everything is still an open question. We simply didn't get enough evidence either way. We didn't rule out the alternative. We never ruled out H1, so it sure wouldn't be fair of us to conclude that H0 is true, because if we haven't ruled out H1, H1 is still just as possible. So what we've got here, it's kind of asymmetrical, but what we're doing with null hypothesis significance testing, the style of significance testing, is we're playing around with the what if of the null hypothesis, saying, if the null was true, would we see something like this? No, our sample is super crazy in that case, so we can reject the null hypothesis. Or we can just say, I don't know. It's, it could have happened under the null hypothesis. It could happen for other reasons. I just don't have enough evidence. We fail to reject the null hypothesis. And those are the only possibilities about the null hypothesis. You either reject it or you fail to reject it, in which case it's kind of still an open question. So try and watch your language. And if your p-value is, below the alpha cutoff of 0.05 or whatever you chose, then yes, you can say you reject the null hypothesis. But if your p-value is above that alpha cutoff, then you just cannot conclude much at all in the standard way of doing statistical testing. You would say, I fail to reject the null hypothesis, and then you leave it at that until more data comes in. And regardless, all of this stuff is probabilistic. So even if we consider a hypothesis to be very, very, very unlikely or very, very, very likely, we will never use language like prove or proves. So even if we accept the alternative hypothesis because we rejected the null, we would still just be saying, oh, I accept it as being very likely, something like that.